Hey, chemistry. It's Wednesday, April 22nd, and I'd like for you to turn your books to 482. 482, table 5, at the top of the page. You've got three theories about acids and bases. The one we've talked about already is Arrhenius' definition, and he says that in a water solution, that an acid is defined as a hydrogen ion producer. You can break a hydrogen ion off of an acid. I've already told you that every acid has hydrogen on the front of it, except for acetic acid, which has it on the end, and it can be detached. All right, bases are hydroxide ions, OH negative, producers. And so those materials are generally formula units, metal, non-metal, ionic bonded, and the water does its job there to break away the hydroxide ions. So that's the Arrhenius definition. We got two others in this section we're going to talk about. Bronsted, Lowry. It says that it doesn't say that it's a hydrogen ion producer. It says it's a hydrogen ion donor. So there must be a base nearby to jump onto. And then the base is a proton acceptor. So the acid is the proton donor, a hydrogen ion, we call it. And the base is the hydrogen ion acceptor. Doesn't that sound an awful lot like Arrhenius? Except that this definition requires that the acid and the base be in close proximity so that that hydrogen ion can transfer. Arrhenius is more standalone type thing, definition. And a Lewis is it's the broadest definition of them all, the Lewis definition, and it says it's an electron pair acceptor. That's the acid. And a base is an electron pair donor. It's just looking backward from Bronsted-Lowry. I'll refer to that again in a minute. And of course, Mr. Lewis is the guy that got us doing Lewis structures. And he's all about electrons and electron pairs and that kind of thing. All right, back to page 478. We're talking about a Bronsted-Lowry acid. And here's the situation. If we take hydrochloric acid and we go ahead and we stick it into water, we're going to get hydronium ions, which you could call protons that attach themselves to water. Protons are H+. So what's H+ called? It's called a proton. What's H+ called? It's called a hydrogen ion. What is H+? It's a hydrogen atom without an electron. It's called a hydrogen ion or a proton. Can I draw it for you? Sure. Hydrogen, element number 1, right up there, has 1 proton. And let's say it's hydrogen 1. Well, here's what it looks like. It's got a proton, no neutrons, and 1 electron buzzing around. When you detach that electron, all you have left is a hydrogen ion, which we call a proton. But that's all that it consists of. And that electron goes on to some other species or free space somewhere. So there you go. Now the question was, what is H+? It's a hydrogen ion, or it's also called a proton. And if this is polar, it attaches to those polar molecules and it forms hydronium ions. And what's left behind is chloride. Now, hydrogen chloride gas in liquid water forms aqueous, dissolved hydronium ions, dissolved chloride ions. That right there can also dissolve in things other than water. Let's take ammonia, for example. And so let's go ahead and put hydrogen chloride in there. Now what happens is this. This detaches and makes it NH4, which is called the ammonium ion. This is hydronium. This is ammonia. Those are words you're going to love, I'm sure. And so what happens, that detaches and attaches to the ammonia. What happens up here? This detaches and it attaches to the water. Why? Because water is polar and it polars it right off. And this is polar and it polars it right off. What does it mean it's polar? I mean, it's got some lone pairs. And what's left behind? Chloride. Aqueous. Aqueous. Now, the question is, what makes this thing up here an acid? Well, according to Arrhenius, it's because it makes hydrogen ions or hydronium ions in water solution. What makes this an acid? Well, it's not a water solution, so according to the definition of, what was his name? The guy we just studied. Arrhenius. According to his definition, this doesn't count as an acid or a base. So it has to be broadened a little bit. The definition is now a Bronsted Lowry. It's labeled B/L. Bronsted Lowry acid is a molecule or an ion that is a proton donor. So do you see the way it donates that proton to this ammonia molecule and makes ammonia? That's what makes it an acid. Not because it forms hydronium ions, but rather because it donates a proton. There it goes. All right. And so you see those Lewis structures that you love so much? Well, there they are in the middle of 478. You can see the HCl attaches to the H2O because it has lone pairs. And the hydrogen ion just gets sucked right into the lone pairs. And then what's left behind is chloride. And if you look right below that, you see HCl with ammonia, and it also has a lone pair. And so it pulls in that hydrogen, completes that bond, and it brings its positive with it, the lack of an electron. And that's why this species is positive. Sometimes that is written with just a plus up there. Sometimes they have little brackets around it. Either way, good convention either way. Water can act as a base when it's up against a strong acid. Water can act like a base when it's up against a strong acid. And water can act as, well, what do we got down here on the bottom of 478? Water can act as an acid when it's up against a weak base. So let's go ahead and do that. Let's just take water and put it up against this weak base. Now what's going to happen? Well, that's the base. So this has got to be an acid. It's a weak acid. Okay, and so what happens here? Well, does one of these hydrogen ions attach? Detach rather, because this is polar. Do you see on the bottom of the page there, 478, you see that lone pair on the top of that ammonia ion, or that ammonia molecule? And so it attaches to that lone pair, and you get Four. Four hydrogens. And what's left behind? When you're ripping a hydrogen off of that, you got hydroxide. And NH4 is positive. So what makes this particular thing an acid? Well, it donates a hydrogen to that weak base. All right, but what makes water a base up here? Well, it's because this acid donates a proton to there. So according to Bronsted Lowry, acids are proton donors, hydrogen donors, and this acid is a hydrogen donor. And bases are receptors. That's the base, and here it's an acid. So we call that amphoteric. Water is amphoteric. That means it's a switch hitter. It can go as a base or as an acid, according to Bronsted-Lowry definitions. Amphoteric sounds an awful lot like ambidextrous. You know, like you can swing the bat right-handed, you can swing the bat left-handed. Yeah, it can go either way. So a Bronsted-Lowry base on 479 is a molecule or ion that is a proton acceptor. I call, according to the Bronsted-Lowry definition, I call the acids the pitcher. You know, like in baseball, the pitcher of the ball, the pitcher of the proton, and I call the base the catcher. That's what I do. Okay, in a Bronsted-Lowry acid-base reaction, protons are transferred from one reactant, the acid, to another. So they got to be in close proximity, and they need each other in order to be a Bronsted-Lowry acid or a base. Okay, on page 479, you got a monoprotic acid. That means an acid that only has one proton, one hydrogen. Hydrochloric acid is one of those. A polyprotic acid, it can donate more than one proton. So an example is sulfuric acid, H2SO4, can donate two protons, and H3PO4, that's phosphoric acid, can donate three protons. So they're polyprotic, so they're diprotic or triprotic, those are polyprotic. Okay, next page, 480. And you can see on the bottom of 480, right above the picture, that H3PO4 is a triprotic acid, and it ionizes in three stages. First, you strip off a proton, and you get H2PO4 negative 1. Then H2PO4 negative 1 becomes the acid in the next stage. You see what I'm talking about? Those reversible reactions down on the bottom of 480 above the picture. And then you strip off another proton and you have HPO4 2 negative, and that becomes the acid in the third stage. And you can still strip off a proton and you end up with PO4 3 negative. The thing that you have the most of is the hydronium ions, because you got three stages. You're producing hydronium ions in every stage. The first stage always produces the most ions, and the last stage produces the fewest. And so the fewest number of ions in that entire three-stage ionization is PO4 3 negative. That's the fewest number of ions. The most is the hydronium ions, H3O positive. Now, what are Lewis acids and bases? I'm just going to go ahead and take a minute to talk about that. I call Lewis acid and bases, we're not looking at protons now. We're not looking at transferring protons. We're looking at electron pairs. And so if you looked at the ammonia molecule on page 481, you'll see in the middle of page 481, you'll see a lone pair next to NH3. Is that a landing pad? That's what I call it. So all Lewis did was look at it backwards from the way that Bronsted-Lowry looked at it. They saw a lone pair here, and that lone pair would be a good receptor for a proton, a hydrogen ion. And so he looked at it as though that lone pair on the molecule was donated to the hydrogen ion. I say it provides it a landing pad so the hydrogen ion can land there. If you go over to page 482, you'll see that Lewis looked at it from this viewpoint, that a base is an electron pair donor. I'm looking at the table 5. A base is an electron pair donor, and acid is an electron pair acceptor. So if you take a look at this hydrogen ion, doesn't it want to have a negative to balance it out? Yeah. And so the ammonia is donating that lone pair to the hydrogen ion so it has a place to land. Up here, this lone pair is donating a landing pad for this hydrogen so it has a place to land. It's donated. And so while Bronsted Lowry looks at it this direction, Lewis looks at it this direction. These guys look at the positive ion flowing over here. This one says the negative lone pair is offering it to them. So that's a backwards thing. All right, I'm going to quit there. You've had 16 minutes. That's probably more than you really care. Stay with me, guys, please.